Oh, hey everyone, I want to talk way too much about exponents, so let's do it. So, an exponent is that tiny little number right up here. See this little guy? That's an exponent. It's a tiny little number we put on another number. The tiny little number obviously is called the exponent. The thing that we put it on is called the base, yeah? Basically, an exponent is how many times you multiply the base by itself. So, I mean, really technically it's how many times you multiply the base times 1, but if I'm saying that 4 to the second power is 4 times 4, that's pretty much the same as saying it's 1 times 4 times 4. So very often we just think about that part of it because the 1 will usually cancel itself out anyway. So I'll talk a little bit more about that later. So basically, giving a number an exponent is also called taking it to that power. So we could say this is 4 squared. We could say the base is 4, the exponent is 2. We could say it's 4 to the second power. And again, exponent tells you how many times to multiply a number by itself. So 5 raised to the second power, or 5 to the 2, that's 5 times 5. H raised to the 4th power, h to the 4 is h times h times h times h. So let's talk more about parentheses. On an exponent problem, it's really important to pay attention to what's inside and outside the parentheses. If an exponent is next to a parentheses, it applies to the entire expression inside the parentheses. If there are no parentheses, the exponent only applies to the number or variable right next to it, whatever it's sitting on. Remember, the exponent is only applying to the base. The base is what the exponent is sitting on directly. So when we look at this guy here, we see the 2 is only sitting on the b, so only the b is squared, not the a. Here the 2 is sitting on the entire parentheses, so both the a and the b are squared. Here the 2 is sitting just on the x, so only the x is squared. This will come out to be negative because of the negative here being multiplied by a positive here, because anything to the second power is always going to be positive. We'll talk about that a little bit more in a minute. Here, the 2 is applying to the entire parentheses, so it's the 2 and the x that are squared, not the negative. So what that'll look like is negative 2x times 2x, or negative 4x to the second power. Now, if the 2 is on the entire thing, this is going to be negative 2x times negative 2x, negative 2x to the second power. Negative times a negative makes a positive, so that's 4. X times x is x squared, so that'll be positive 4x squared. So you can see how many different answers we can get just by grouping the exponent on different things. So keep an eye out for your parentheses. This is also really important when we play monomial versus polynomial, which I know you've all played with me in a previous video or in person. So if you think about this here, if we have 2x squared, what does that mean? That means 2x times 2x, which gives us 4x squared. This is very different than 2x squared, which is just 2x squared. Now let's think about the difference between this guy here, 2 plus x squared. Well, that's just doesn't simplify at all. That's just 2 plus x squared versus this, 2 plus x squared. So this is very important to notice because a lot of people want to say, oh yeah, just like I did here. I gave this, I squared this, I got 4, I gave this here, and I got x squared. Oh, no. By the way, this is my pet peeve. Don't do this. If you give the exponent to both, you might think this is 4 plus x squared, 2 squared plus x squared, which would be 4 plus x squared. This. No. Why? That's not what this means. What this means is 2 plus x times 2 plus x. It's 2 plus x squared. And remember, when you multiply a binomial, 2 terms times another 2 terms, another binomial, a binomial times a binomial, we FOIL, which we'll talk more about in another video. But what that means is we multiply our first guys together. That's 4. We multiply our outers together. That's positive 2x. We multiply our inners together. That's positive 2x. And we multiply our last together. That's positive x squared. When we combine our like terms, we're going to get 4 plus 4x squared. 4x plus x squared. This is what we want. This is yes. And you can see that that's different from this guy up here. So remember, if it's a monomial, you can absolutely give the exponents to both of the parts. If it's a polynomial, make sure you FOIL it out. Very important to remember. So when we combine exponential numbers, we want to make sure that they have the same base. This is very important, and I'll show you why in a second. So when we multiply exponential numbers together that have the same base, we add the exponents. We add the exponents. So if I have 2 to the 5 times 2 to the 3, it'll be 2 to the 5 plus 3, or 2 to the 8. Let's see why. So if I have 2 times 2 times 2 times 2 times 2, that's 2 to the 5th power, right? 2 to the 5th power. And then I have times 2 to the 3rd power, 2 to the 3rd power, which is 2 times 2 times 2. If you think about what we have now here, we have all to the same base, and there's a faster way to write 2 times 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 2. Well, that's 8 2's multiplied together, or 2 to the 8. So it makes sense why we would collect these guys together, because we really are, all of the math that we're doing is all multiplication. This is 5 2's multiplied together and 3 2's multiplied together, all multiplied together. So we have a way to write that, and that's 2 to the 8. So again, it makes a little bit of logical sense why we add them, because what we're really doing is just counting up how many 2's are multiplied together. Now, when we divide exponential numbers that have the same base, we subtract the exponents. So if I have 2 to the 5th on top and 2 to the 3rd on bottom, and we're dividing them, that will become 2 to the 5 minus 3, or 2 to the 2. Let's see why. If I have 2 to the 5 on top and 2 to the 3 on bottom, and I'm dividing them, I have 2 times 2 times 2 times 2 times 2 in the numerator, and 2 times 2 times 2 in the denominator. But let's remember, when I have 2 over 2, what is that equivalent to? 2 divided by 2, that's 1. That cancels out. 2 over 2, that's 1. That cancels out. 2 over 2, that's 1. That cancels out. And what am I left with? I'm just left with these guys. These don't cancel out. In the numerator, I have 2 to the 2. So again, you can see why the subtraction makes sense there. What I'm really doing is canceling out these ones on the bottom from these ones on top. And if there's some extra on top, fabulous. That's what we're left with. Now, when we raise an exponent to another exponential number, we're going to multiply the exponents. We're going to multiply the exponents, which makes sense again, because if I have 2 to the 5 to the 3rd power, what I'm going to get is 2 to the 5 times 3, which is 2 to the 15. So let's get the receipts on that. Ready? We have 2 times 2 times 2 times 2 times 2. That's 2 to the 5 right there. But we have that 3 times multiplied by itself. So let's do it again. 2 times 2 times 2 times 2 times 2, and 2 times 2 times 2 times 2 times 2. So that's 2 to the 5, 3 times multiplied times itself. Amazing. Well, let's count up how many we have. Let's count up how many we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So basically 2 to the 5, 3 times is 2 to the 15, or 15 2's multiplied together. So again, you can see here a lot of these exponential rules are really easy to intuit when you write them out. So when in doubt, you can always write them out. However, I strongly encourage you to memorize these rules. Memorize these rules, because pretty soon you're going to be doing them with exponents that are variables, or exponents that are fractions or negative. And if you don't have these rules, it's going to be really confusing how to use them. So for example, if I say 2 to the 2x over 2 to the 3 equals 2 to the 10, and I want to find out what x equals, again, this is not super intuitive to simplify until you remember, oh, they have the same base. They're exponents. I can then subtract them. So I get 2 to the 2x minus 3. Again, same base, and they're divided, so we subtract the exponents. And that's going to equal 2 to the 10. Now, if the bases are the same on each side of the equation and they equal each other, well, then my exponents have to be the same. So I can set these guys equal to each other. 2x minus 3 equals 10, and now I can solve. Add 3 to both sides. 2x equals 13. Divide both sides by 2. I get that x equals 13 over 2, or 6.5, or 6.5, or however, 6.5 rather, or 6.5, or whatever you want to say there. So again, we can see why this might not be intuitive, just something you can just think about and see how to reduce, or why it would be hard to write it out, because like, how do you even write that out? But if we use our rules that when we divide exponential numbers with the same base, we subtract the exponents, we can see how we can set this up based on the rules without having to think about it all the way through. All right, so here's some warnings for you. Warnings: you can add variables with the same exponent and the same base, but you can't add bases with different exponents. So to look a little bit more deeply into this guy, this is okay. Why can we combine these guys? Well, they're what are called like terms. Let's investigate what a like term means. We're going to talk about this more in the algebra video, but a like term means you have the same base with the same exponent. So a lot of people might say, but Donna, isn't this have a base of 2x and that have a base of 7x? No, no, no. Please remember, the base is the thing that the exponent is on. So if this 2 is on the x here, the x is the base. And if the 2 is on the x here, the x is the base. There's no exponent on the 2 and the 7. Well, I shouldn't say no. There is an exponent, but it's just 1. It's not the same exponent as that on the variable. Remember, anything to the 1 is just 2 or just 7, right? If this happens, I'm going to show you the kind of algebra that explains it. Please don't add like terms this way, you'll be here all day. But if I factor out an x squared, what would I be left with? I'd be left with just the 2 over here plus 7. Again, if you're confused about how I factored that out, just think about it as undistributing, like I'm taking the x squared out, I'm unmultiplying it and putting it on the outside instead. Now you can see these are just numbers here that I have. 2 plus 7, well, that's just 9x squared, and that's where we get the 9x squared from. However, I would like you just to know that when the bases are the same and they have the same exponents, they're like terms, so you can add or subtract their coefficients and put them with the variable. You can think about this as, oh, I have 2x squareds, and I'm adding them to 7 of the same thing, 7x squareds. Well, 2 of something and 7 of something make 9 of that same thing, so make sure the x squared comes along with it. Now, this is a little bit different. This is not okay. Remember, we said when we multiply exponential numbers together that have the same base, that's when we add the exponents. We do not do that when we're adding the exponential numbers together. This would have to be a multiplication in order for that to equal. That's not what that is. Basically, if you think about it, this is 2 times 2 times 2 times 2 times 2 plus 2 times 2 times 2. Does that equal 8 2's multiplied together? No, it's 5 2's multiplied together and 3 2's multiplied together, and they're being added, not multiplied. That's why this guy here, we don't add the exponents. This symbol here means does not equals. Keep that in mind. They do not equal each other. There's actually not much we can do to simplify this besides factoring out, like say a 2 to the 3. If I factor out a 2 to the 3, I'd be left with 2 2's here because I took out 3 of them, right? And just 1 here because you multiply 1 times 2 to the 3. So again, that might be easier to simplify by hand, but again, you're not going to see a ton of this on the SAT. So again, just a reminder, all these rules only apply, the rules we just talked about for multiplying, dividing, and raising, only apply to exponential numbers with the same base. If you're given exponential numbers to different bases, very important, try to get them into the same base. Let's explore this a little bit. I can rewrite numbers that are equivalent to other numbers as exponents. For example, 16 is equivalent to 4 to the 2. It's also equivalent to 2 to the 4. 125 is the same as 5 to the 3. Again, I'm rewriting numbers with different bases, right? This was 125 to the 1, now it's 5 to the 3. They're equivalent, so we can change the form of the number without changing its value by writing it as an exponential number. So we'll see why that comes in handy in a minute. let's talk about negative exponents. So a negative exponent is the same as the reciprocal or the flip, top and bottom, of the base with the positive exponent. That is 1 divided by a number with a positive exponent. So I'm going to talk way too much about this because I think people find this confusing. So let's get an intuitive sense of these negative exponents. So say I get 2 to the 4. What's that? Punch that out on our calculator. Well, that's 2 times 2, which is 4. 2 times 2, which is 4, times another 2, which is 8, times another 2, which is 16. Okay, that's 2 to the 16. Okay, so 2 to the 4 rather is 16. If I lower the exponent and make it 2 to the 3, what would that be? Well, that's 2 times 2, that's 4, times 2, that's 8. So that's 8. It looks like when I lower the exponent, I'm dividing by 2. Well, that makes sense because the 2 to the 4 is 2 times 2 times 2 times 2. This is just 2 times 2 times 2. How do I get from here to here? Well, I lop off one of the 2's. How do I do that? I divide by 2. These will cancel. Yes? So basically, every time I lower the exponent, I remove a factor of 2. I divide by 2. Or you could think every time I raise an exponent up 1, if I increase the exponent by 1, I multiply by another 2. But we just talked about that, so we know about that. Let's talk about going in the opposite direction. What if I had 2 to the 2? Well, that'd just be 8 divided by 2. That's 4. Yeah, that is what 2 to the 2 is. How about 2 to the 1? Well, that would just be, rather 2 to the 1. Well, that would just be 4 divided by 2. Well, that's 2. That checks out. How about 2 to the 0 then? We're going to talk a little bit more about this rule in a minute, but what would that be? Well, we lowered the exponent by 1, so I have to take 2 and divide it by 2 again, which is 2 divided by 2. That's 1. And you'll find that that's always the case. If I have 3 to the 1, that equals 3. 3 to the 0, that'd be 3 divided by 3. That'll give us 1. Anything to the 0 always equals 1. Important to know. Now, what if I decreased my exponent again? Well, 0 minus 1, that's 2 to the negative 1. Well, then I'd have to take that 1 and divide it by 2 again, and I'm going to get 2 to the, wait a minute, that's not right at all. I'm going to take 1 and divide it by 2. I'm going to get 1 divided by 2, or 1/2. I'm going to make these a little smaller because I am running out of room a little bit. Let me make this a little smaller. Here we go. We can zoom in a bit and get us a little more room. Okay, so let's try that again. Well, how about 2 to the negative 2? Well, what's that going to be? I'm just going to take my number and divide it by 2 again. I'm going to get, what's 1/2 divided by 2? Well, let's remember, keep, change, and that's over 1. So if I flip it, it's 1/2 times 1/2, or 1 times 1, 1 over 2 times 2, 2 squared, or 1 over 4. All right, that's going to be 1 over 4. All right, 2 to the negative 3. We lowered the exponent again. We divide by 2 again. What are we going to get? 1 over, well, again, that would be 4. Dividing by 2 is the same as multiplying by 1/2. So that's 4 times 1/2. That's 1 over 8. Okay, so are you noticing a pattern? One, you might notice that going this way and going this way kind of gives you the same in the numerator and in the denominator. You might notice that. You might notice that if I go 1, 2, 3, I get to 8 here in the numerator. If I go 1 to negative 3, I get 8 in the denominator. Let me show you what happens if I write these guys in a slightly different way. I'm going to move this over so you can kind of see what we're going to do here. Take these out because I think you know how to multiply now. So if we take this, guys, I can also write this as 1 over 2 to the positive 1, or 1 over 2 to the positive 2. 2 to the positive 2, that's the same as our 4 here, right? 8 is the same as 1 over 2 to the positive 3. You can also see this pattern that the negative in the numerator becomes positive in the denominator. Negative up top becomes positive down below. Negative over here becomes positive down to here. If you're like, Donna, I don't see a numerator, just remember everything that's not a fraction is always, you can say, over 1. So again, what we did is basically move it down to the denominator and make it positive. Okay, so if you think about it, if a positive exponent means multiply by me 4 times, multiply by me 3 times, multiply by me 2 times, The negative exponents can't mean multiply. It's the negative of multiplication. Negative here doesn't always mean like negative numbers. Here it means the opposite of multiplication. What is the opposite of multiplication? It's division. Let me write that down. What's the opposite? Opposite of multiplication? It's division. And this is really important to notice because what that means is my negative exponents mean the opposite of multiply by me. They mean divide by me. So here, this says divide by 2 one time, and that's what we did. This is divide by 2 2 times, that's what we did. Divide by 3 2 times, that's what we did. And if we think about this here, we can say then x to the negative 3, if I put that over 1, would mean 1 over x to the positive 3. Divide by me 3 times. Now, what would that mean if I had a negative in my denominator? What would that mean? Well, that would mean, remember, dividing in the denominator, that would be 1 over divide by x 3 times, and dividing by 1 over x, it's the same as 1 times, dividing by 1 over x cubed is the same as 1 times x cubed over 1. Remember, dividing by anything is the same as multiplying by the reciprocal. And what's that going to be? Well, that's just going to be x cubed. So, again, you can see dividing in the denominator is the same as multiplying in the numerator. So this is very important to remember. And now we can also apply all our exponent rules to these negative exponents. Shrink this down a bit. We can apply these to our negative exponents. So if, say for example, I have x to the 5 times x to the negative 2. Remember, when I multiply exponential numbers that have the same base, what do I do to the exponents? We add them. We're going to add them, and we're going to get x to the 5 plus negative 2. We can do that in our calculator. We can know that adding a negative is just going to be the same as subtracting, so that'll give us x to the 3. Now, what if I wanted to rewrite this as a positive exponent? Well, that would be 1 over x to the positive 2. And if I multiply that by x to the 5th, well, remember, multiply the tops together, multiply the bottoms together, I'm going to get x to the 5th over x to the positive 2. Oh my goodness, look, it's the same thing. Remember, when we divide exponential numbers, we subtract the exponents. We're going to get x to the 5 minus 2, which is x to the 3. Same thing, just different ways of writing it. So, if anybody is feeling a little bit overwhelmed by this, please go back and rewatch again, or call or text me, message me, email me. I am here to explain this in a totally different way if you like. In fact, I'm going to show you one of those ways now. When I work with my really little guys, I don't need them to understand what these exponents are. I just want them to have a little fun with it. So you know what I tell them? I tell them a story about when I used to go to the mall with my grandmother as a kid, and I would say, okay, this is my grandmother. This is 8, okay? And this is me, tiny little Donna, being taken around by grandma. She's carrying me. That's why I'm up a little bit, okay? And you can see, am I feeling happy today? Oh, no, I'm feeling pretty negative, pretty grumpy. Why? It's because we're at the mall, and we're up top. We're up top at the mall, on the top floor. And guess what? That's where all the frilly dresses is. But I wanted to go to the back in the day it was Sports Chalet, the little sports store, and play with all like the fun sports equipment and the balls and the bats and all the fun stuff down there. So I wanted to go play. But my grandmother was having me upstairs, and I was pretty grumpy. I was pretty negative about it. So what do I want to do? What would make me happy? Well, if I could go downstairs. So that would be 1 over 8 to the positive 2. Now I'm happy in the denominator. So if you're grumpy in the numerator, what would make you happy? Move you down to the denominator, and then you become positive. Now, if I was a different sort of kid, maybe someone took me down to the bottom floor and I was a little bit grumpy to be down there with my grown-up. You know what could have made me happier? If you moved me up to where all the pretty dresses were upstairs, right? So, again, if you're negative in the denominator, that's positive in the numerator. So, again, you can always rewrite negative exponents as positive ones. So let's just play that game for a second. So say I were to have x to the 2, y to the negative 3, z to the negative 5 over a, b to the negative 1, c to the 4. And I wanted to rewrite this with only positive exponents. Well, let's think about this. Let's take it number by number. Let's say our x squared. Well, that has a positive exponent. That means it's happy where it is. So we're going to leave it. Let's take our y to the negative 3. Ooh, that's a grumpy y. You know where it wants to be? It'll be happy if I put it in the denominator with a little positive exponent. All right, let's take a look at that z to the negative 8. Ooh, it's grumpy up there. It wants to go downstairs. So let's put it down on the bottom floor, that negative 8. Then will become a very happy positive 8. All right, let's get our denominator. This a, you're like, Donna, where's its exponent? I can't tell if it's happy or sad. Remember, if you can't see it, it's always a positive 1. All right, looks like it's happy where it is. Let's leave it right where it is. Happy positive exponent. All right, let's look at this next guy over here. We have b to the negative 1. Oh, negative b. It's so grumpy. All right, let's move it to the numerator, make it nice and happy. Okay, and again, because it's a positive 1, we don't have to write it. And I don't have to write that positive 1 exponent on the guy in the denominator anyways either. So now let's see about that last little guy. Let's see about that last little guy. That's c to the 4. Looks pretty happy to me. It's a nice positive exponent, so let's leave it where it is. So when we simplify this, it'll look just like this. It'll look just like this now with all positive exponents. So again, you can just notice happy, sad exponent. Where do you want to move it? All right. Anything to the power of 0. Does everybody remember what anything to the power of 0 is? It always equals 1. So 7,892,000 to the 0 power equals 1. So let's take a look at a fun one that could use that. Say I said 2 to the 3x plus 5 equals 1. What would you know the exponent would have to be in order for it to equal 1? Well, it can't equal 2 because 2 to the 2 is 4. It can't equal 3 because 2 to the 3 is 8. It can't equal 2 to the negative 1 because that would be 1/2. What would make it equal 1? If our exponent was 0, which means we could set our exponent equal to 0 and say 3x plus 5 equals 0. Oh, well, that will allow me to solve for x. If I subtract 5 from both sides, 3x equals negative 5. Divide both sides by 3. I get that x equals negative 5 over 3. Woo! That will only happen if I can notice that any number raised to an exponent, if it comes out to be 1, that exponent must have been 0. We've talked a lot about exponents. Now I want to talk about roots and radicals. You might be thinking, Donna, what do those have to do with exponents? Well, let me talk way too much about it. So a root or a radical is you can kind of use those words interchangeably. The radical is actually this symbol. The root is the operation that we're doing. So I'm going to talk a little bit more about this, then we can talk about these rules that we have up here. Basically, if I take a number and I square it, in fact, let's make it 3. 3 squared. That's going to come out to be 3 times 3, which is 9. This square, we can think about it as a function, something that we did to the 3. I could do it to a 4. I could square it, and then it would mean 4 times 4, and that would be 16. I could do it to a 5. Put the tiny 2 on a 5. It means 5 times 5, and 25. So while all these numbers are different, right, this symbol right up here means the same thing for each thing. It's something that I'm doing to the 3, the 4, the 5. That's called a function. It's a procedure that I'm performing on the 3, the procedure I'm performing on the 4, the procedure I'm performing on the 5 that gives me this result. So if that's the case, then I must have something also to undo the procedure. So now let's take the results of our procedure, that 9, that 16, that 25, and I want to unsquare it. Well, if I unsquare it, then 9 will go back to being a 3, the 16 will go back to being a 4, and the 25 will go back to being a 5. So what will that be? What procedure? Well, we've decided that if I make this funny symbol, that means unsquaring. Now this symbol here has some implied value here, which is 2. That little 2 tells us the function that we're undoing. We're undoing the square function. And because we use this guy a lot, we don't write the 2 in there. Just like we don't usually write the 1 on just numbers that are to the first power, we don't write the 2 here. That is just implied that there's a 2. And just like we don't write the 1 underneath integers all the time, we don't write the 2 here, but it's implied. So that means we're unsquaring it, and that'll go back to saying, okay, what do I square to give me 9? It's 3. What do I square to give me 16? It's 4. What did I square to give me 25? It's 5. Now that's not the only exponent that has what's called the inverse operation, like the undoing function. Say I did 3 to the 3rd power. Well, that would be 27. 3 times 3 times 3. That gives me 27. Or 4 to the 3rd power. 4 times 4 times 4. That's 16 times another 4. That's going to give me 64. Or 5 cubed. That's 5 times 5 times 5. Oh, my phone's looking a hot mess today. 5 times 5 times 5. That gives us 125. But what if I wanted to undo that function? What if I wanted to undo it? Well, let's think about how to undo cubing something. Well, we do what's called the cube root. There we go. And then I'd be asking myself, well, what did I cube to give me 27? Well, it was 3. What did I cube to give me 64? That's 4. What did I cube? What times itself 3 times gives me 125? Well, that's 5. We're uncubing it. Another way to think about this is, remember, 27 was 3 to the 3. 64 was 4 to the 3. 125 was 5 to the 3. That 9 up here is 3 to the 2. This was 4 to the 2. This was 5 to the 2. And anytime the index, that's what this little number is in here, even if we don't write it, matches the exponent, they'll cancel each other out. So did you see that? When they cancel, they just go back to being what they were in the first place. These guys cancel. These guys cancel. These guys cancel. So and say you wanted to undo, make this smaller, give me a little more room. I'll try that again. So if I wanted to cancel out something to the 4th power, well, I would cancel it out by taking the 4th root of that. So if I, again, take my little 4th power and put that right in here, they'll cancel each other out, and we'll go back to being x. They're the undoing function. Now, there's another way to write these guys, which we'll talk about in a second, but let's see some fun things that happen when we do something like square root of x times square root of x. Well, that would just be square root of x times itself, or square root of x squared. Remember, this guy here and this guy here are the opposite operations. So they're going to cancel each other out, boom, boom, and we're going to be left with just x. So again, whether I'm taking the square root of x squared or squaring the square root of x, these guys are opposite functions, and we're going to go back to being x. So let's look at our little rules here. A root is just the inverse or the opposite of its corresponding power. A square root is the inverse of a square. A cube root is the inverse of a cube. A 4th root is the inverse of the 4th, and so forth. That means doing the same thing will cancel each other out. You can see some good examples here. Radical x times radical x just goes back to being x. And then if I square root a square, we get x. If I cube root a cube thing, it gives me x. If I take the 4th root of something to the 4th power, it gives me x. Now, this is the next bit I want to talk about. A fractional exponent is the same as a root. So let's explore that a little bit. So you might be thinking, Donna, this seems like a very weird, archaic symbol to go making all over everything. Absolutely, math agrees. So let's write them as an exponent, because in a way they are. They're just the opposite procedure of an exponent. So if I have the square root of x, remember we said there's an implied 2 here and an implied 1 here. If I want to write that as an exponent, I could write that as x to the, let me color code this, x to the 1 over 2. The power goes in the numerator. The index of the radical goes in the denominator. Okay, the power of the radical goes in the denominator. So we can say to ourselves, the power of the thing underneath the square root, it's called the radicand, but you don't need to know that for this test, divided by the root. So what would it be if I was taking the cube root of x to the 5th power? Well, I could write that as x to the power, that's our 5 power, over our root, which is 3. Now you might be thinking, but Donna, why would I want to do such a silly thing as this? It's a little bit, like, can I just write it as a radical? Yes, but remember, our radicals don't have all those lovely rules we had for exponents, or another way to say that is, because our radicals are exponents, we can use our exponent rules on them, and that's easier to see when written as an exponential number. So say I had that lovely cube root of x to the 5th times the 5th root of x to the 2nd. And I'm like, well, how would I simplify this? I don't know, this is super confusing. Well, let's remember, we can write that as a fractional exponent. Power over root, so 5 over 3 times x to the power over root 2 over 5. And remember, when we multiply exponential numbers together that have the same base, what do we do to the exponents? We add them. And this is something we can do in our calculator. And we're going to get x to the, what would that be? 31 over 15. If anybody was wondering how I did that, I'll show you really fast. We have 5 over 3 plus 2 over 5. Our common denominator will be 15. So if that's a 5, multiply the top by 5, that's a 3, multiply the top by 3. So the numerator will end up being 15 plus 6, or 31. So 31/15. Anyways, we did that really, really fast just by converting it to exponents. Now, if you think about it, I can rewrite this back as a radical if I want and say, okay, remember, it's power over root, so that's x to the 31 in the 15th power. Well, that's kind of fun, right? So, or I can say, simplify this radical, because if you think about what this means I have 31 x's underneath my radical, 31 x's. So I can actually write that a different way. And then we're going to explore this idea of simplifying radicals. So here, if we take a look at this, I could rewrite that. Is it not the same to say as x to the 15 times x to the 15 times x to the 1? Wouldn't that be the same? Because remember, when I multiply exponential numbers together, I add their exponents. 15 plus 15 plus 1 gives me 31. Now, if I'm taking the square root of each of these, I'm taking the 15th root of x to the 15th, the 15th root of x to the 15, and the 15th root of x to the 1. Now, tell me about this guy and this guy. They're gonna cancel each other. That's just gonna be x. This guy and this guy, they're the same as each other. They're just gonna cancel. That's just gonna be x. They're all multiplied together times the 15th root of x to the 1. Well, let's think about this. X times x, that's x squared, times the 15th root of x. Wow, that's a lot simpler, isn't it? And it gives me these nice numbers out here, which I always like. So again, a way to simplify a radical. Now you might be thinking, but Donna, why are you allowed to, let me put this x back over here. Why are you allowed to break up this radical into these 3 different pieces? Why are you allowed to do that? Well, I'm going to remind you of a lovely exponent rule that we had. Remember, 2x squared, because it's a monomial, I can give my exponents to both parts of that, right? Make it 2 to the 2, x to the 2, or 4x squared, because it's a monomial. One thing in here, no adding or subtracting. Check it out. Monomial, one thing in there, right? And if I rewrite this as an exponent, check out what happens. That would be x to the 15th, x to the 15th, x to the 1, raised to what power? Well, if we think about this as to the first power, to the 1 over 15. 1 over 15. Let's use, so again, a monomial raised to an exponent. What will we do? We can just give our exponent to each of those parts. Now let's remember, when we raise an exponent to another exponent, what do? We multiply. So this will be x to the 15 sorry, this would be a 15 in the denominator here to match this guy right here. 15 times 1 over 15, well, that's 1. Then we also have this guy, x to the 15 to 1 over 15. Well, that's just going to be to the 1. And here we have, oopsies, x to the 1. So 1 times 1 over 15, well, that's just x to the 1 over 15. And again, if I look at how I simplify this, x to the 1, x to the 1, we add those exponents, that's x to the 2. And if I want to write that last one as a radical, 15 is the exponent, is the radical, and 1 is the exponent. So we have lots of different ways to think. All right, I did promise to talk way too much about this, so let's do this. So all the rules that apply to exponents also apply to radical or rational exponents, exponents written as a fraction. So again, consider the difference between this and this, right? This is a monomial, this is a binomial or a polynomial. Remember, when I have a monomial raised to an exponent, I can give that exponent to both of those and say it's 2x times 2x or 2 squared x squared. See how I gave the exponent to both parts? And we get 4x squared. Versus if I have x plus 2 squared, that would be not x squared plus 2 squared. Oh, no, it's a binomial, so we cannot give the exponent to both parts. We'll have to FOIL it out, right? We'll look at x plus 2 times x plus 2, or x squared plus 2x plus 2x plus 4. If we combine our like terms, we get x squared plus 4x plus 4. You can see that's not the same as this guy, right? Remember, these guys are just fractional exponents, fraction exponents. So that's 4x squared to the 1/2. And that's the same as 4 plus x squared to the 1/2. Again, this exponent is being given to monomials. We can give it to both parts. We can take 4 to the 1/2, which again, you can punch into your calculator, or you could think about that as the square root of 4, which is 2. And here, when I raise an exponent to another exponent, what do I do to the exponents? We multiply. So that's going to be x to the 2 times 1/2. And what's 2 times 1/2? That would be to the first power. And if something's to the first power, that'll just give us x. So again, and it's like taking the square root of both of those parts individually. We can also think about that as the square root of 4 times the square root of x squared. What's the square root of 4? It's 2. This radical and that square will cancel each other out and put us back to being x. Now, remember, we cannot do that to things that are polynomials. These guys are added together. So are we going to call this 4 to the 1/2 plus x squared to the 1/2? Absolutely not. That is a big no. Don't do that. Just like we don't do this. Don't do that. So what will we do instead? Absolutely nothing. There's no way to simplify this that you need to know for the SAT. So don't stress out about it. If there was a way to like factor it or get it into a different form that was a perfect square of something, great. Maybe we could simplify it, but not here. Don't do that. Yes, monomials, yay, good for simplifying. Polynomials, boo, not good for simplifying. Okay, so we'll keep an eye on that. So let's talk about this quotient rule for radicals. The quotient rule for radicals means basically what we were just talking about. If I have a monomial here, again, things that are multiplied or divided, I can apply the radical or the fancy exponent to both the top and the bottom. So let's check this out. Say I had the square, or let's make it fancy, the cube root of 27 over 125. Well, that means I could take the cube root of 27 and divide it by the cube root of 125, and that would give me 3 over 5, an easy way to simplify it. Another way to think about this is if I have them separate, I can put them together. Say I have the square root of 4 divided by the square root of 2. Well, this can be a little bit tricky because it's like, well, this simplifies to 2. And the bottom, though, is irrational. It doesn't simplify, right? So let's see what we can do here. I can put them under the same radical because they have the same index. They're both square roots. 4 over 2, I can simplify that. 4, that's just 4 divided by 2, that's 2. And then I get my answer is just the square root of 2. So again, we can break them apart like we have here into a top and a bottom, or if they're apart, we can put them together. We also have the product rule for radicals. You're going to see this one quite a bit on the SAT. Do you see how these guys have the same index, but their radicands, the thing underneath, aren't the same? If they have the same index, we can put them under the same radical and put them together. So here's an example. Say I have the square root of 9 times the square root of 4. Well, that's the same as the square root of 9 times 4, which is a square root of 36. And what do we square to get 36? Well, that's just 6. Okay, let's check it out. Remember, square root of 9, that's 3. Square root of 4, that's 2. If I multiply them together, do I get 6? I sure do. Absolutely right. So you can put them together, but keep in mind, we can also break them apart. And that's the rule that we were using to simplify our radicals. Remember when we had the 15th root of x to the 31? And we rewrote x to the 31 as x to the 15th times x to the 15th times x to the 1st. And all that was to the 15th root. Remember, we broke it apart. And again, that's because of our product rule of radicals. We could take the 15th root of x to the 15, the 15th root of x to the 15, and the 15th root of x to the 1st. And again, these guys will simplify x, these guys will simplify x, and this guy does not simplify because it's to the 1st. But if I wanted to, I could write it as a fraction exponent and say x to the 1 over 15 or something like that. Again, it's all about changing the form without changing the value. But again, we're using this product rule here to help us simplify those radicals. So what if our variables are in the exponents? And what if we have different bases? Well, we looked at a problem like this earlier. If 2 to the a plus 10 equals 2 to the 3a, what does a equal? Well, let's see. If the bases are the same and they equal each other, they need to be raised to the same power in order for them to be the same number, right? Which means that our exponents must equal each other. We can say a plus 10 equals 3a, and then we can solve, subtract a from both sides, and that gives us 10 equals 2a. We can divide both sides by 2, and we get that our a equals 5. That allowed us to solve for something, a variable in our exponent. Now, what if our bases aren't the same? Ooh, the formatting on this, not cute. Let me fix it. Let's see. I'm gonna fix this one too when we get there, and this one too. Okay, sorry for that. Let's make this 9. What do we say? 9 to the 5. 9 to the 5, just like that. Okay, let's think about this. Now, do you think I could say that x equals 5? No, I can't say that because the bases aren't the same. Now, if I wanted to make the bases the same, I absolutely could. Now, you might remember, we can rewrite 9 in a creative way as 3 to the 2nd power. Why did I choose 3 to the 2nd power? Well, so our bases will match each other. So let me just rewrite this. 3 to the x equals, quote unquote, 9 to the 5. But let's write 9 in a creative way. I'm not going to write it 9 like this. I'm going to rewrite it like that. And now look what happens. That's our 9. 9 is the same as 3 squared. But it's not just 9, it was 9 to the 5th power, right? It was 9 to that 5th power. So tell me, what do we do when we raise an exponent to another exponent? We multiply. So that means this is the same as 3 to the x equals 3 to the 10th power. Okay, check that out. Tell me, if the bases are the same and they equal each other, tell me about those exponents. They also equal each other. So now we can say x equals 10. So again, the important thing to notice here is 9 to the 5th is the same as 3 to the 10. They're just written in different forms. This one, 3 to the 10, is more useful to us than 9 to the 5th because it matches our base of 3 that we're already given. Now listen, the SAT makers aren't monsters. They didn't give you 17 as a base here or 123 as a base here. They gave you something that could be related to 3. Now, I do have a caveat here, which is if you don't know your multiplication tables, it will be incredibly difficult for you to see when bases match. Here is your call to action. If you don't know your multiplication tables, learn them. And this is coming from a woman who did not learn her multiplication tables till she graduated from college. When I tell you math got so much easier after I memorized them up to 14, I cannot emphasize this enough. And if you're in high school right now, or in college, or in middle school, and you're watching this video, and you're like, hey, I don't think I really need to do this. Listen, I didn't think so either. But I'm here to tell you, yourself from the future will thank you if you go ahead and memorize them. Memorize your multiplication tables. Drop me a little note if you need help with that. I got lots of help for that. Okay, let's do some practice with these exponents. All right, so let's take a look at what we have here. We have two things going on. We have this guy times this guy, and this guy being raised to that guy. Okay, which do we do first? Well, let's remember PEMDAS. PEMDAS is our order for doing mathematical operations. P is for parentheses. We do that first. E is for exponents. M and D are for multiplication and division. Remember, they're just flip sides of the same coin, so they're on the same level. A and S is addition and subtraction. Again, flip sides of the same coin, they're on the same level. This is what we do first, and then we go to what we do last. So here we have exponents or multiplication. Which one do we do first? We're going to do our exponents first and then our multiplication. So when I raise an exponent to another exponent, what do? We multiply. So that's going to be a to the 6th. And now we have two that are multiplied together with the same base. What do we do to the exponents? We add them. A to the 5 plus 6, that's a to the 11. All right, let's look at the next one. Here we have 3 to the 2 raised to the 1/2 power. Now, there's a couple ways to do this. I can say, well, my 1/2 power, that's just a radical with an index of 2 and an exponent of 1. Well, when you take a radical square root of something squared, they'll cancel, and I'll just get 3. But we can work this as a fraction exponent as well. Take a look. When I raise an exponent to another exponent, what do? We multiply. So we get 3 to the 2 times 1, which is 1. There you have it. 3 to the 1, we can get it both ways. Now let's see about this guy. Here we have things that are multiplied and things that are divided. Those are on the same level, so it doesn't rightly matter which one we do first. So I like to clean up my numerator and denominator before I do anything else. So what I'm going to do here is multiply these guys together. And when I multiply exponential numbers that have the same base, I add the exponents. So that's going to give me x to the 7 on top and x to the 5 on the bottom. So 7 on the top cancel out with the 5 on the bottom, so we subtract the exponents. And that'll give us x to the 2nd power. Now you might be thinking, but Donna, could I just divide first? I wouldn't do that. It's kind of hard to see how you would divide. The whole thing is being divided by this. So simplifying this makes it easier to see what we're dividing by. All right, let's look at this next one. This one gets a lot of people. We're going to raise the exponent before we do the subtraction. So let's make sure we do this. Tell me, what's being squared? The 3, the x, or both? It's in parentheses, so we should say both, yes? So and it's a monomial, so I can give my exponent to both pieces here, or I could think about that as 3x times 3x, which is 9x squared. So that's going to give me 2x squared minus 9x squared. And again, because these are like terms, they have the same bases and the same exponents. We're going to add or subtract their coefficients. 2 minus 9, that's negative 7, x squareds. Ooh, now this next one's a little spicy. I have both a fraction and a negative. Now we'll remember, negative means that exponent is grumpy as heck. What would make it happy? If we moved it down to the denominator. So that would be the same as 1 over 9 to the 1/2. Now that's something we can punch out on our calculator. Or, if you'll remember, this just means a radical, 1 over the square root of 9 to the 1. And what is the square root of 9? That's just 3. A lot of people will look at this problem and think that my answer should be a negative number. But remember, that negative is not a proper negative. It doesn't mean subtraction. It doesn't mean negative. It means the opposite of multiplication, which is what? Don't multiply by 9 to the 1/2. Divide by 9 to the 1/2. Very good. All right, Let's see this guy. Tell me what's being cubed. Is it the negative, the 2, the x squared? Well, all of it's in parentheses, so it's the whole darn thing. This is going to be negative 2x squared times negative 2x squared times negative 2x squared. Well, negative 2 times negative 2 times negative 2, that's negative 2 cubed. X squared times x squared times x squared, that's x squared cubed. And again, this guy here you can punch out on your calculator, but a negative times negative will be negative. 2 times 2 times 2 will be 8. When you raise an exponent to another exponent, what do? We multiply. That's x to the 6th power. All right, let's look at this next one here. Ooh, I see we have bases and they equal each other, but our bases aren't the same. What do we do when the bases aren't the same? We make them the same. How can I write 8 as a 2 to the something? 8 is just 2 to the 3rd power. So again, this problem says 8 to the 13th equals 2 to the x, but I'm not going to say 8 like 8. I'm going to say 8 like 8, like 2 to the 3. So now when I raise my exponent to another exponent, what do? We multiply. So that's going to be 2 to the 39 equals 2 to the x. Ah, yay, now my bases are the same and they equal each other. So what can we say about the exponents? The exponents are the same. We can say that x equals 39. Now this next one gets a lot of people because it's kind of intense. It's just a bunch of things multiplied together. But if you think about this, this is just 5 times y times 2 times 1, 2, 3, 4 x's times y times 3 times x times y, right? So let's just collect it. Because of the commutative property of multiplication, it says I can multiply anything in whatever order I want. 2 times 3 is the same as 3 times 2. So I can take my numbers and put them first. 5 times 2 times 3. I can put all my x's next. So that was these guys, 5 times 2 times 3. I can put all my x's next. That's 1, 2, 3, 4, 5, 6 x's multiplied together. 1, 2, 3, 4, 5, 6 x's multiplied together. And I can grab my y's. 1, 2, 3, 4, 5 y's multiplied together. 1, 2, 3, 4, 5 y's multiplied together. And then we can just simplify. That's going to be 10 times 3 or 30. This is going to be how many x's multiplied together? I think we got 6 x's multiplied together, so that's x to the 6th power. And 5 y's multiplied together, that's y to the 5th power. So this is my answer, 30 x to the 6th, y to the 5th. Now, if you're like, Donna, I really don't want to write that all out, that's absolutely fine. You can take it from right here. 5, you can just remember that we're just multiplying these all together. So 5 times 2 times 3, that's 30. And we'll remember x to the 4th times x to the 2nd. We add the exponents to get x to the 6th. And here we have y to the 2nd power and y to the 1st power. Remember, we have it to the 1st power there if it's not written. And then we have y to the 2nd power, 2 plus 1 plus 2. Well, that gives us 5. All right, now this guy here, you'll notice, is a little bit similar to the one that we had up here. Do you guys see the similarity there? We have 2 things multiplied together and one of those things is being raised. So 2 things multiplied together and one of those things is being raised. Let's do this the same way. Let's think PEMDAS, exponents first and then multiplication. So let's just copy down our first factor there, the first bit in our multiplication there. And then let's take the other guy and raise it. So remember, when I raise an exponent to another exponent, this is a monomial, so I raise each one to the 3rd power. So 8 raised to the 3rd, we multiply, we get a to the 24. B is negative 1 raised to the 3rd power. Negative 1 times 3 is negative 3. Again, that exponent rule makes it nice and easy. And again, c's to the 2nd raised to the 3rd. We multiply those exponential numbers and we get to the 6th. Now, we're just multiplying our numbers together. These are all multiplied together. 3a's multiplied together times 24a's multiplied together. Well, that's 27a's multiplied together times, we have 4b's multiplied together times a negative 3b's. Remember, when we multiply exponential numbers together that have the same base, we add the exponents. 4 plus negative 3, that's just 1. And then we have, oh, I made that a b, that should have been a c, I'm sorry about that. So we have c to the 10, 10c's multiplied together times another 6c's. Well, that's going to be c to the 16th, and they're all just multiplied together. Again, when in doubt, write it out. Don't highly recommend doing that instead of memorizing your rules, because who wants to write out 24 A's? But you know, when in a pinch. All right, let's look at these guys. We've seen simplifying the top like this. Let's do it the easy way, right? Let's do our coefficients first. 5 times -2, that's going to give me -10. And then I have 1x times 3 more x's. That's going to be x to the 4th power. That's 4 x's multiplied together. And then I have 3 y's times another y. Well, that'll be 4 y's multiplied together. And then in my denominator, I have x squared y to the -2. Now, this is also with a 1 here. So if I simplify our numerical coefficients, that's just going to be -10 divided by 1 is -10. When I simplify my x's here, remember we subtract the exponents when we divide exponential numbers that have the same base. That's going to be x to the +2. 4 minus 2 is 2. Now this guy's a little bit spicy, but let's take a look. This is y to the 4th divided by y to the -2. So remember, this y to the -2 is grumpy in the denominator. I could just move it to the numerator and put y to the 2 up here. Then I would say, oh, that's 4 y's times another 2 y's. That's y to the 6th. But I can also keep it in the denominator and just use my subtraction rule. Remember, when I divide exponential numbers that have the same base, I subtract the exponents. If I do 4 minus -2, that's 4 plus 2. That's also 6. So either way we do it, we're going to get the same answer. Well, that's a lot about exponents. So let's pause here with this for today, and we're going to pick up with absolute values in the next video.